Tonight we are going into the math of chemistry. So welcome, good evening. I am Erin, and welcome to Wyzant's Getting Ready for High School Chemistry. So last week we did the introduction to chemistry. This week we're doing the math of chemistry, specifically scientific notation, significant digits, calculations and conversions, and an introduction to dimensional analysis. So these are things that you will encounter within your first couple of weeks of high school chemistry, and it's important that you are solid with these foundations, especially the math. It can look a little overwhelming for some students. So if you see it now and you see it again when your class starts, it should help you a little bit. All right, so we're gonna get started. So the first thing I like to get into is scientific notation. So you've probably seen this before in your math classes. This is when you use the notation times 10 to the something. So we use scientific notation as a way of expressing really small or really large numbers. In chemistry, scientific notation is kind of crucial because we're talking about numbers of atoms, which is in the millions, trillions, times 10 to the 23rd, really, really large numbers. And so instead of writing a lot of zeros, we use scientific notation. And then we're also talking about things that are extremely small as well. So scientific notation is used a lot in chemistry. It looks really intimidating, but it's not that hard. So I'm going to go over what it is, how to write numbers in scientific notation, and then how to conduct math with the scientific notation as well. So scientific notation, a way of expressing really small or really large numbers. It always involves a number between 1 and 10, or I should say 1 and 9.9, followed by times 10 to the something. So the power is dictated by how many times the decimal point has been moved to change the number to a number between 1 and 10. So that's the important part, is scientific notation always involves a number between 1 and 10, and then times 10 to some number, some power, indicating really how large that number is or how small. So here's a couple of examples. These are standard notations here. So these are numbers that are kind of large, and they get a little bit difficult to write over and over again in expressions, especially if there were more zeros after this. So we like to minimize them and put them into scientific notation to make them a little bit more manageable. So you can imagine, for this one, 42,000, we imagine there's a decimal here at the end. So if you don't see a decimal, you kind of assume there's a decimal at the end, there's a hidden decimal. And so the trick is to make this number smaller, not actually make it smaller, but record it as smaller so that it dictates, or it shows a number between 1 and 10. So I'm going to change this to 4.2, and then the number of times I've moved the decimal point is my exponent. So I moved it 1, 2, 3, and 4 times. And so I change it to a number that says 4.2 times 10 to the 4th. So typically, if you're moving the decimal to the left, the number, the exponent over here, will be positive. And then if you're moving the decimal to the right, then the exponent will be negative. So for this one, 0.0508, I'm going to move this decimal, which is actually written here, 2 times to get this number to a number between 1 and 10. So 5.08, and then I moved it 2 times 10 to the negative 2. Now, a trick that I like to show students is, because sometimes we don't remember, did I move it to the right? Is that positive? Is that negative? So I kind of like to just remember, and this is helpful for converting as well, if you're making this number smaller, because we're going from 42,000 to 4.2, then we have to make this number larger. And vice versa, if we're making this number larger, because we're going from 0.0508 to 5.08, so we're making this number larger, we have to make this number smaller. And you can imagine you're starting at times 10 to the 0, basically, and so you're either going forward or you're going in reverse on the number scale. So that's kind of how I like to teach this. I find that students remember that a little bit more, and so they don't get so caught up in the left and right and positive and negative. But here's just little points here. Like I said before, the exponent is positive if the decimal place must be moved to the left to get it into scientific notation, and then the exponent is negative if the decimal point is being moved to the right. So again, make this number smaller, this number goes up. Now, like I said, I like to explain it that way because sometimes you're changing numbers that already have, they're kind of already written in some form of scientific notation, like it might be 42 times 10 to the third, and you have to change this into scientific notation. So again, if you kind of remember that, make this number smaller, this one has to go larger. So it would be 4.2 times 10 to the fourth. And so that's helpful, I find, for some kids to remember that way, especially if you're trying to change numbers that already have exponents into scientific notation. So let's do some practice with scientific notation before we move on to the next concept. So convert the numbers to scientific notation. So again, if you see a number like this is like 24,700, we imagine the decimal point is here at the end, and we're just going to change this number to a number between 1 and 10. So we stop at the 2.4. I wouldn't leave it as 24.7 because that's not a number between 1 and 10. So we would get 2.47 times 10 to the fourth because I moved the decimal point 4 times. And then in this one, again, we're trying to get a number between 1 and 10, so 1, 2, 3. So I'm making this number larger, so I have to make my exponent smaller. So 7.85 times 10 to the negative 3, because we moved it 3 times. And then the last one, 2, 3, 4, 5. Again, I'm stopping to where it shows a number between 1 and 10, so 1.2 times 10 to the fifth, because I'm moving it 5 times over. I'm making this number 5 times smaller, so I'm going to make my exponent 5 times larger. Okay, and then sometimes your teachers will have you convert into standard notation instead. So the same thing can be thought for this. So these are numbers that are already in scientific notation, and we're kind of converting them into standard notation. So why do we do this? Just so you can kind of grasp the size of these numbers. So if you see 4.4 times 10 to the fifth, this is a really large number. So again, you can kind of use the same tactic. You're trying to minimize this number, so you're trying to get this one to 0, so you have to make this one smaller, which means you have to make this one 5 times larger. So this turns into 1, 2, 3, 4, 5. So here's my decimal point, 440,000. So this is a really large number. We wouldn't really like to write this in equations, so we would rather put it in like this instead, which is why we like scientific notation. 2.95 times 10 to the negative 2. So again, you're trying to make this number 0. You're trying to get out of scientific notation. So we're going to make this number smaller because we're making this number larger. So 0.0295, and see how the decimal moved twice. And then 6 times 10 to the negative 6. So we're going 6 times this way to 0.000006. So again, these are good examples as to why we like to write in scientific notation instead of standard notation, but it's helpful to be able to convert between both so you can practice with this. Okay, so scientific notation is not that difficult to put numbers into scientific notation. I find that some students, though, are very intimidated when it comes to math with scientific notation. So this is something that you will do in chemistry a lot, is doing math with scientific notation. And I always see the same mistakes that kids make. They will attempt to put this in their calculators because they're so intimidated by these numbers. And what the calculator does is it does exactly what you put into it. So if you're not putting parentheses in the correct spaces, your numbers will come out incorrect. I know it's hard to believe because you're using a calculator. So I teach my students to shorthand this and do it correctly and try to minimize the amount of calculator usage. So you can easily do math with scientific notation. Even though it looks really intimidating, it's not that bad. So I'm going to go through both signs and how to do it because there's 2 different ways to do it. So if you're trying to add 2 numbers or subtract with numbers in scientific notation, it's kind of like fractions. In fractions, we like to keep the denominator the same, and we we can like add or subtract if our fraction denominators are the same. So in scientific notation, it's very similar. As long as we can convert the numbers so that they have the same exponents, like times 10 to the fourth and times 10 to the fourth, then we can just perform the sign, meaning addition or subtraction, with the main numbers and carry the exponent. So I'll show you the example of that in a second. And then with multiplication or division, the tactic is different. So perform the sign, either multiply or divide with the main numbers, and then you either add the exponents if you're multiplying, or you subtract the exponents if you are dividing. And then of course, for both of these, remember to keep the final answers in proper scientific notation. Okay, so going up here, we'll do an example up here. So this is 5 times 10 to the 5th plus 2 times 10 to the 4th. So these are two different exponents. So we can't just add 5 plus 2 yet. We have to make one of these into the same exponent. So which one should we choose to change? So we can change this one first. So I'm going to change 2 times 10 to the 4th, and I'm going to try to make this 5 so that it's the same exponent as this one over here. So if I want to raise this number, that means I have to decrease this number. So I'm going to change this to 0.2 to get this to 5. So I've got 0.2 times 10 to the 5th plus 5 times 10 to the 5th, and then I can just add these numbers and carry the exponent. So it turns into 5.2 times 10 to the 5th, and that's my answer. So again, it's actually, if you can mentally think about this, it's easier to do this in your head or on paper versus a calculator, because typing in all the exponents and then the parentheses and hoping you have it right. And if anything, you can still use a calculator. If you're decent with that and that's a reliable form for you, by all means use a calculator, but you should be able to look at this and kind of mentally check to make sure that this answer is kind of what you thought it would be if you're using a calculator. So it's helpful to kind of know how to do this in your head. And then another example, so this is subtraction. So again, the same thing, we're just going to subtract the large numbers once we get the decimals to be the same. So this time I'm going to change this number to depict this, not the decimal, the exponent, to depict the exponent. So I'm going to change this to 4. So I want to lower this number, which means I have to raise this number. So I'm going to lower this by 1, which means I'm going to move the decimal over by 1 to make this number 10 times larger. So this turns into 70 times 10 to the 4th minus 3 times 10 to the 4th. So this you can just perform the sign then with your main numbers. So 70 minus 3, 67 times 10 to the 4th. Now, the problem with this number is that 67 is not in scientific notation. So you just need to move the decimal over 1. So it's 6.7 times 10 to the 5th, because I'm making this number 1 smaller. So I have to make this number 1 larger. So that's the biggest thing with all of these signs. Now I find that addition and subtraction are a little bit more tedious than multiplication and division. That's just my opinion. Although I think a lot of students would agree. But the takeaway is, of course, make sure that your answer is in scientific notation as well. So 6.7 times 10 to the 5th. Okay, and then let's do a couple examples for multiplication and division. So perform the sign with the main numbers, either add exponents for multiplication or subtract for division. So this one's very cut and dry. You basically perform the sign, so 5 times 10 to the 5th times 2 times 10 to the 4th. So I'm going to do 5 times 2, which is 10, and then 5 plus 4, because this is multiplication. So 10 times 10 to the 9th, and then of course I'm not done yet because I have to change this to a number between, I know I said number between 1 and 10, it's really number between 1 and 9.9. So I'm going to change this to 1, so I'm making this number smaller, so I have to make this one 1 larger. So it's going to be 1 times 10 to the 10. And then division, same thing, but you're dividing and you're subtracting. So 4 divided by 8 would be 0.5, and then 7 minus 4. So 0.5 times 10 to the 3rd, and then we're just going to make this a 5, so I'm making this one larger, So I have to make this one smaller. So 5.0 times 10 to the second. So this looks really complicated, but it's not. Like once you kind of learn how to perform these signs in scientific notation, these questions become a little bit easier. And like I said, your teacher will probably allow you to use a calculator, but you should know, or you should be able to do mental checks to make sure that these numbers are coming out pretty much correct. Okay, so the next topic that I think we should go over really quick are just a really quick trick on metric conversions, because we talked about scientific notation, and then to talk about metric conversions, so there's a couple of ways to do these. I find that most students, when they get into chemistry, do not know this super easy way to be able to convert between metric units. So much like scientific notation, the metric system is used to report or use prefixes to convert the base units into units that are more appropriate for the item being measured. So what does this mean? I know this looks really intimidating. It's not. We use different units to report different measurements. So if our measurement is extremely large, we tend to try to use these units over here, kilo, hecto, deca, to report the unit, because these are more for larger units. So if we've got like 5,000 meters, we can, instead of saying 5,000 meters, we can report this in kilometers instead. So we could just say 5 kilometers instead of 5,000 meters. Or if we have units that are really small, like 0.005 meters, we could instead report this in milliliters and say 5 milliliters. So it's kind of like scientific notation, where you're just simplifying the number and you're reporting it in a different unit to make the number a little bit more manageable. So this chart looks really intimidating, but it's not. It's just kind of showing you these are different units that we use. This is the thousands, hundreds, tens, the unit, so your grams, your meters, your liters, the unit without the prefix in front of it. And then this is tenths, hundredths, thousandths. And this is like the base conversion, but I'm going to show you a really easy way to convert between metric units. Now this does not work if you're converting between like standard and metric units. That's a totally different way to convert. But this will solve your problems in a pinch if you're trying to go from like liters to milliliters, or grams to milligrams. So common units in chemistry, we talk in terms of grams and milligrams and milliliters. So these are common units or liters that you'll have to convert between all the time, liters, milliliters. So there's easy ways to do this. So I use this mnemonic. It's called King Henry doesn't usually drink chocolate milk. There's definitely other mnemonics to go with this. However, you can memorize KHDUDCM, but this is a very common one that a lot of teachers will use. So if you can remember that, then you can remember the order of the units, and then you can easily convert between the metric system. So I'll show you some examples. I'm going to write the mnemonic up here, KHDUDCM. So remember, this is King Henry doesn't usually drink chocolate milk. So you can remember this, remember the U, and then you just write out the first letters of all of these, KHDUDCM. So the beauty of this, or the simplicity of this, is we can use this to kind of go between units. So I'll show you some examples of what that means. So if you have 5,000 grams, you're in the unit right now, because grams doesn't have any prefix in front of it. It is the unit. So you're here and you need to get to kilograms. So you want to convert 5,000 grams into kilograms, because this is a large number and it would probably look better if it was in kilograms, because it would be simple, or more simple than 5,000. So I'm in the gram unit right now, which is just a plain old unit, and I want to get here to kilograms. So I'm going to move my decimal 1, 2, 3 times over. So I'm going to do the same thing with my number, 1, 2, 3. And then my kilogram number is going to look like 5. So 5 kilograms. So that's simple. There's really no math involved. Like I said, when we talk about dimensional analysis at the very end of this lesson, I'll show you a different way to do this. But this is what I find students are not too intimidated by, is if they can use this mnemonic and they can just kind of move the decimals around. Same thing with these liters. So this is a really small number for liters. It would look better if we converted it into milliliters. And so we're here at the unit. So you always place your decimal to the right of the letter because that's kind of where the invisible decimals are. So we're going from liters, which is at the unit spot, to milliliters, which is over here. So 1, 2, 3. So I'm going to move my decimal 1, 2, 3. So I get 6.5 milliliters. And then same thing with 3 million milliliters. So this would look better as kilometers because we can move our decimal over and simplify the number. So I'm here in millimeters and I want to get to kilometers or kilometers. So 1, 2, 3, 4, 5, 6 times over. So I'm going to do the same thing to my number. My decimal point starts here, 1, 2, 3, 4, 5, 6. So this is really just 3 kilometers. So see how we simplify this really large number into just 3, and then we just report a different unit. And that's kind of why we have all of these different units. And then we've got hectograms. So this is not a very common unit in chemistry, but I talk about it just so you can see the concept. So 0.0000587 hectograms. So again, we're starting here in the H area, and then we're converting into milligrams. So 1, 2, 3, 4, 5 times over. So do the same thing with your decimal, 1, 2, 3, 4, 5. So really you get 5.87 milligrams. So all of these numbers, we were able to convert into more manageable numbers by just changing the metric unit. So this is kind of why we have this metric system, is so that we can report different base units into units that are appropriate for the item that we're measuring. So easy conversions for metric. All right, significant figures is almost the last concept. And this is important. I see students get really intimidated by this concept. It's not difficult. It does take a little bit of memorization. So significant figures are essentially measured digits that we take on the scale and we report them to a number of significance, essentially. So if we're looking at this ruler, typically in chemistry, we will look at this and measure 5.2 because we see the 2 and then we guesstimate to one more digit. So this 3, 5.23, the 0.03 centimeter is an estimated digit, the 0.2 centimeter is a known digit, and the 5 centimeter is a known digit. And so we get this answer of 5.23, which gives us 3 significant digits. So we don't want to overestimate the precision of this, like we wouldn't say 5.230. We only guesstimate to one digit that we can't really see on the tick marks. So why do I talk about this? Because this is important to know what a significant figure is. So even though we have an estimated digit here, this is still significant and it kind of sets the tone to how accurate our number actually is. So in this number, we have 3 significant figures, which is fairly accurate. So when you are looking at significant figures or just numbers in general in chemistry, you should be able to look at a number and you should be able to say, how accurate is this number? So you should be able to count how many significant digits are in that number. And so we have rules to do this. Go through these rules. So here's a number with a bunch of different digits in it. And we want to try to look at this and say, how many significant digits are there in this number so that we can kind of gather how accurate this number is. So there's 3 main rules to significant digits. So all non-zero digits are significant, which means all non-zero digits. So these 3 are definitely significant. Captive zeros, which are zeros between 2 significant figures, are significant. So captive zeros are zeros that are in between 2 non-zero digits. These are significant. And then leading zeros at the beginning of a number are never significant. So any zero in front of a non-zero digit is never significant. And then the 4th rule, I know I said 3, I meant 4. The 4th rule is talking about trailing zeros. So zeros after a number, so these ones. So trailing zeros are only significant if there is a decimal somewhere in the number. So significant at the end and a decimal point is present. So in this number, obviously the non-zero digits are significant. The captive zero digits, the captive zeros are significant. And then the trailing zeros in this particular number are significant because there is a decimal somewhere in the number, but none of the leading zeros are ever significant. So this number has 1, 2, 3, 4, 5, 6, 7 significant digits in this number. So that's the goal at first, is to count how many sig figs are in a number. So we can check this. How many sig figs are in each number? So this is 1, 2, 3, 4. So these both are trailing zeros, and there is a decimal, so we count them as significant. So 4 digits. Numbers in scientific notation always have the correct number of sig figs in the number that's reported, and that's it. So 4.7, this is only, we don't have to worry about what this is. We don't have to convert it into standard notation. We just say, okay, there's this number, so we count the sig figs of this number, which is 2, both non-zero digits. Okay, this one, all of these are considered trailing zeros. So we look to see if there's a decimal, which there is none. So we only count these as significant. So 2 sig figs. Doesn't mean that this number is only 34. It just means that it's not a very accurate number because it's only accurate to 2 sig figs. And then this one, these are leading. So we don't count these. We do count the 34. And then these ones are significant because there is a decimal. So there's 4 total. And then this one, non-zeros and captive zeros. And this one is not significant because there's no decimal in the number, so only 5 digits total. Okay, math with sig figs. So this is the other part about sig figs, is knowing how, this is kind of the reason that we did this whole unit, is knowing how to conduct or knowing how to do math with significant figures. So when you're adding or subtracting numbers, this is important that you're able to report your answer to the correct amount of sig figs. So when you're adding or subtracting numbers, you round your answer to keep the fewest decimal places. So you look at the numbers that you're adding, for example, like 5.5 plus 1. And if this number, like 1, doesn't have anything after the decimal, then you just round the answer to a number with nothing after the decimal. So technically this would be 6.5, but I would round this to 7 because there's nothing after the decimal of 1. And I always round my answer to the weakest number in terms of sig figs or fewest decimal places. So for addition or subtraction, we look at the answer choice with the least amount of decimal places after the decimal, least amount of numbers after the decimal. And then for multiplication or division, we round answers to keep the fewest significant figures total. So we look at our answers to determine, we look at our numbers to determine which one has the least amount of sig figs, and then we model our answer after that. Okay, so for example, this one is 3.48 plus 2.2. So I always do these in the calculator first, and then I round my answer. So this is technically 5.68, but I don't keep this. I round this because this number only has 1 number after the decimal. So my answer should only have 1 number after the decimal. So really this would be 5.7. And then for multiplication and division, round answers to keep the fewest sig figs. So this number has 3 sig figs. This one has 2. So my answer should have 2 sig figs to model after the weakest number here. So my answer is technically 12.8, but if we rounded this to 2 sig figs, this would be 13 total. Okay, so let's go through this really quick. How many sig figs are in each number? So we're just checking these 150, and there's a decimal point here. So this is not a period, this is a decimal point. This indicates that all of these numbers are significant, including the trailing 0. This one is 4 because we only look at these numbers and they're all non-zeros. This one is a little tricky. It's a really large number, but there's only 5 sig figs total because we don't care about these because there's no decimal place in the number. And then this one, these are leading zeros, so we technically only have 2. And then round the answer to the correct sig figs. So 34.5 times 23.46. So this is technically 809.37, but I'm rounding this to 809 because I'm modeling it after this number with 3 sig figs. And then 123 over 3, so the answer technically is 41, but I'm rounding this to 40. and then 23.888897 plus 11.2. I'm rounding this to 35.1 because I'm modeling after this number here. And then 2.5 times 2 minus 3, so this can be done in steps. 2.5 times 2 is 5.0 minus 3, so this has no numbers after the decimal, so I rounded to 2. Okay, so finally, the last concept on here is dimensional analysis. So I'm going to go through this really fast because I know we're running out of time. So dimensional analysis is also called factor label method or unit factor method. You might have heard this in another class, or maybe you did this in the class before this. It's a very fancy term for basically just using mathematical units to convert between different numbers or between different units. So fancy term for mathematical conversions that doesn't involve memorizing. So it's a nifty way of setting up an equation so that you don't have to memorize. Do I multiply? Do I divide? And it's a way to convert one unit into another with a conversion factor that's given. So you probably won't do dimensional analysis right away, but this will set you up for when you do encounter it in class. So I'm going to do a really easy example, convert 54 seconds into minutes. Now, this is easy because you know a minute equals 60 seconds. This is something you've seen before, and you probably know, oh, I just multiply, or I just divide 54 by 60. But the way we set this up in terms of dimensional analysis can show you like how you can convert other units that you maybe haven't seen before. So we start with the given, which is 54 seconds, and we always write the unit so that we know where to go from here. So the unit has to be used because we're going to draw out a fraction. So we say 54 seconds times, and then we draw a line here. And then we always write the unit that we start with on the bottom because we're trying to get rid of that unit and get to the next unit, which is minutes. And so here's where we write our conversion factor. So we put 1 minute at the top because we're trying to get to minutes, and we're trying to get rid of seconds. So 54 seconds times 1 over 60. And so really this is just 54 over 60, which equals 0.90 minutes. So we got rid of the units. And we got rid of the units of seconds and we got to minutes. And then this basically tells us exactly what we have to do. So we didn't have to memorize 54 divided by 60. We just say, okay, times our fraction, set up our units, put the unit that we started with on the bottom, and then we get 54 divided by 60. So I'll show you 2 more examples and then we can be done, and I will check the question. So how many centimeters are in 45.15 inches? So this is a common conversion, maybe not in chemistry, but more like math. Again, you'll be given a conversion factor. This is probably not something you have to memorize. So you always need this in order to complete your dimensional analysis problem. So 451.5 inches is your given. We start with writing that, and then we draw our fraction, and we put the unit that we start with on the bottom to cancel it out, and then the unit that we're trying to get to on the top. So we're going to put inches on the bottom, and 1 goes with inches, and then centimeters on the top because that's what we're trying to get to, and the 2.54 goes with centimeters. So again, we've got 451.5 times 2.54 over 1, which is really just 451 times 2.54, and so we get 1,147 centimeters. So the last example, how many atoms are in 3 moles? So this is what you will deal with in chemistry. Now, a mole is just another type of conversion factor, but it involves an extremely large number. 6.02 times 10 to the 23rd atoms are in 1 mole. So this is like, a mole is like, there's 6.02 times 20 to the 23rd pieces of paper in a mole. A mole is the same thing as a dozen, as a ton. It just means it's an expression of a really large quantity. So if you have 3 moles, that's your given. And then here's your conversion factor. So again, your unit that you're beginning with, moles, goes on the bottom of your fraction to cancel it out. And the unit that you're trying to get to, which is atoms, goes on the top. Now that you know how to do math with scientific notation, you can see that this is really just 3 times 6.02. Anytime you see a number like 3, you can imagine that it's times 10 to the 0, because 10 to the 0 is 1. So really you can do this in your head. 3 times 6.02, which is roughly 18 something, and then 0 plus 23. So 3 times 6.02 is 18. I round this to 2 sig figs because I'm reflecting this number here, 3, which is 2 sig figs, times 10 to the 23rd. So I carry this because I just do 23 plus 0 because it's 3 times 10 to the 0. And then I'm changing this into scientific notation, which is 1.8 times 10 to the 24 atoms. So this is later on in the year, which is mole conversions. But just so you kind of get a handle on dimensional analysis, it's very simple. It's really just structuring your equation so that your units cancel out. And so if you can see this and you kind of understand this now, you will be this much more ahead when you encounter it in class, and you can get a head start with that. Okay, so I'm gonna stop for questions and look at the Q&A. And it looks like we don't have any questions. So I will see you guys next week.